So yesterday I have just shown you that an example of the decision trees, but we need to understand the concept right behind that. So let us understand the concept in the decision trees, guys. So coming to the decision trees, we know that we have just gone through the classifier characteristics. When we had discussed about the classifier, the very first classifier that we understood is a KNN classifier. KNN classifier means K nearest neighbors. Okay, so where it has gone through the segmentation or the classification of the data. Okay, so the way that the K nearest neighbors has segmented the data with a curvy line or the quite fit line in between, whereas SVM or the logistic regression has its own plane line. Okay, it's a linear plane line which is segregating the data, right or wrong? So the next one is, this is the simple model, which is a K nearest neighbors model, where it is really faster to fit and show the data. So coming to the logistic regression, see, generally for the logistic regression, this is how it works. We have a formula, you could see that this is how the way that it is going to segregate. See, we will say whether it is true or false, or 0 or 1. In the yesterday's data set that we have gone through, the according to the advertisements that we have made, based upon the salary and age and the gender, whether the respective people are gonna buy my product or not. Okay, if the respective people are going to buy the product or not. So based upon that one, we will try to classify the stuff using the logistic regression model. If you could understand, the logistic regression model defines that the 0 or either 1. So hence, the formula, the mathematical calculation will be completely based upon 1 divided by 1 plus e power minus beta naught plus beta 1 x plus e, which is nothing but a linear formula, guys. You have to observe this one. Okay, linear formula. Okay, so beta naught plus beta 1 plus error is going to be the one which is going to be used in order to understand between the line how it is going to perform. Here in the logistic regression model, the fitting is little bit slow when it is compared to the KNN model. Okay, but the prediction is a little bit faster and it will calculate the expected value based upon the given parameters. Okay, so now this is the introduction to the decision trees. Now let us try understanding this data set. Okay, so guys, in this current example, you could clearly understand the very first column is showing you something called a day, and the very second column is showing you something called an outlook. Third one is temperature, humidity, and wind. So based upon the given parameters, we need to understand, based upon the situation, can we play the tennis or not? Okay, for example, let us go ahead with a day one. Outlook is very much sunny, temperature is hot, humidity is high, and wind is weak. Okay, so can't play the tennis. So the answer is no. Okay, the result is no. Oh, outlook is overcast. Overcast means it is more than sunny. and it is hot, and the humidity high, weak, but still it was S. Okay, so we need to try to understand the kind of data it was given over here. It is rain. Outlook is day 4 is rain. Okay, and temperature is mild, humidity is high, and wind is weak. See, wherever you could see, you could observe clearly that okay, there are different aspects that we could always consider. Okay, we need to take the decision whether to play the tennis or not based upon the given understanding. So we wanted to predict whether to play the tennis based on the temperature, humidity, and wind and outlook. Okay, so here you could see that temperature, it's greater than or equal to mild. Okay, greater than or equal to mild. So when the temperature wanted to be, I mean, if you wanted to take a decision based upon the temperature, you can take a decision whether to play the tennis or no tennis. Okay, why? Because temperature is equal to mild means it is acceptable. Greater than mild represents whether to play tennis or not. So we can always try segmenting the data based on the different features that which is going to predict the result. Now let us try understanding this concept a little bit more. So here you could observe temperature. See, you generally this decision trees relies on the different parent nodes, root nodes, and the child nodes. The very top one can be considered as a root node, and the next immediate down to the line can be considered as a child node, okay, or the parent node. Whenever a node which is required to consider as a parent node, we need to understand that there might be a child node below that. Understand all of you? Okay, now temperature is greater than or equal to mild, and humidity is equal to mild, normal. Okay, so then whether to play tennis or not. See, earlier we have just only one condition, whether the temperature is greater than or equal to mild. Now at this point of time, we have one more, whether the humidity, okay, if temperature is greater than or equal to mild, if it is acceptable, okay, when we are avoiding the no tennis, and then we need to accept the humidity then. What about the humidity? Is it normal or not? Based upon that, again, you need to decide whether to play tennis or not. Okay. So here the trees are always there that predict the categorical results. That's why it is called as the decision trees. Understand all of you? Okay. So now, generally regression trees predict the continuous values. Something like this. This is a clear-cut example. Why? Because we have mentioned in the previous slide the trees that predict the categorical results. But now we are seeing in a different prospect, which we can consider them as a regression trees. So here the regression trees predict the continuous values. What exactly the continuous values about? Slope and elevation in Himalayas. Okay, here you can take it as an elevation. If it is less than 7,900 feet, then check the slope. And if the less than slope is 2.5 degrees, then you have to check like whether you are going to have the precipitation 13.67 inches or the 48.50 inches. So these are all the continuous values. Okay, so these values can be always considered in order to depict how exactly the regression trees will look like. You could see that this is the way that the regression tree is going to depict you the data, okay, in a regression format, whereas we are completely dealing with the values here, numeric values. And you could clearly observe when the decision tree is going up with the root node and the child node basis, and the way that the maximum depth that you can clearly understood how exactly it is going ahead across very much clearly. Okay, how the depths and ups and downs are going on, the maximum depth which can be considered 5 here. Here it is the maximum depth is C. Based upon the maximum depth, that you can always try to pick the points or the data points which are going to be the continuous values. Okay, here how do we build a decision tree? So very first thing is we need to first select a feature, and then we need to split the data into a binary tree, and then splitting continuous until that you are going to get the outcome of it. Okay, so how long that you need to split the nodes? Okay, unless and until you are going to end up with one result is the important thing that you have to observe. Okay, once, see here we have the couple of statements that we can always rely on when we are looking after this kind of stuff. So when, until when that we can do keep on splitting this one, we will keep on splitting this one until we reach a maximum depth, until we reach the only one class which is going to be remained at the end. Otherwise, until a performance metric is achieved. Okay, likewise we have different formats. So building the decision tree is nothing but something just like understanding the end point. Okay, each and every point that we need to try understanding the best split across. We need to try to understand the best split at each and every stop. So how we need to understand where to split and how we can understand it is going to be the best split. Okay, so we need to understand the information first of all, how we are making a split, and from there on then we need to perform whatever that we want. So here, how this information gain is going to happen is a very important thing. Okay, so here we have an equation which is going to be E of t is equal to 1 minus max I of P of I or T, whatever it is. Okay, this is a error equation for the classification. Okay, let us forget about this particular equation, whatever it was mentioning over there. Rather than, you can see clearly the splitting based on the classification error. 8 people say yes, 4 people say no. Okay, and if at all if you are going ahead, 6 people yes and 2 people say no. Okay, and 2 people say yes, and you are giving the higher priority towards the total number of people who are giving saying yes, or total number of nodes that they are saying yes. So here you could see the classification error before, which is 1 minus 8 divided by 12. Why? Because 8 divided by 8 plus 4, total number of statements that what we are going to take it in consideration. Okay, which is going to be the 0.33. Okay, so then the classification rate, which is classification error on the left hand side, is 0.50. Okay, and the classification, so here whenever we have the classification error which is 0.50, the information was lost on the small number of data points. Means the information is good in the higher number of data points. Here, see here we have 0.33 and here it is 0.50 and here you could observe it is 0.25, which is 1 minus the 6 by 8. So we can clearly understand 0.333 minus, okay, 4 divided by 12. Why 4 divided by 12, guys? Means which is saying no, okay, into 0.55000, sorry, which is not saying no, it is this one. Okay, how many number of s and no? Okay, so here no 10 is okay, minus means you are going to deduct these two things, okay, from the top one. So and also minus 8 divided by 12, okay, from this one existing one, so where you are going to make it as 0. So it should be equally split across these three nodes itself. If at all, if you are going to get a value, then you are missing somewhere here. We need to clearly observe this 0.33 is none other than the one which you have identified the classification error. If you are going to add up all these three things together, you should be getting the 0 as a value. Here you should clearly understand that you have done that one for 4 divided by 12 into 0.500 minus 8 divided by 12. Here it is 8 divided by 12, okay, into 0.25. Why? Because these two things have been, these two things have been derived from the top one or the decision node. Okay, so now we have understood the classification error. Okay, there are no further splits here, and here we can clearly understand the end nodes are not homogeneous. Means we need to have the homogeneous nodes at the end. So let us go ahead and try a different metric. So here we do have something called an entropy. Okay, this is the splitting based upon entropy. Entropy is the one, here you could see the equation, okay, through which that we will generally go ahead through the evaluation of the entropy. Sigma I is equal to n, okay, and p of I comma log p of I. Okay, so now let us see this one, how the entropy is being calculated. Minus 8 by 12, just to substitute the values, minus 8 by 12 log 2 of 8 divided by 12 means how many decisions are made based upon yes, minus 4 by 12 log 2 of 4 by 12. Okay, so 0.91 is the entropy before. Once we cross that entropy, on the left hand side it is 1.0 and on the right hand side it is 0.81. So if you can make the same calculation again, you are going to get the right side entropy as something just like this, 0.0441. Okay, so here the splitting based upon the entropy allows the other splits to occur rather than making it as a 0. Here we have got something called a 0 here in the error classification. Okay, classification error change. Here you could observe that you are coming up with some sort of a value. So here what is happening, you are trying to reach the goal. Why? Because we always try to get only one single value at the end of the nodes. So here the entropy is going to give us some sort of classification error, okay, which is showing us something that you can still derive from the existing one. Okay, so here the classification error versus entropy means like why the classification error won't made it the any homogeneous prescription, whereas entropy made it. What exactly the difference here? The classification error is a flat function with a maximum at center, something like this one. Take a look at this one. 1 minus, okay, all of you, 1 minus p of I. That's max of p of I. Means you are going to take a one single value, okay, and you could see the classification error is looking something like this. Okay, If you are going to take a plot between the purity and the error, this is how it is going to looks like. So you could see the center represents the ambiguity as 50-50. Okay, you could clearly understand the matrix that the center is far away from the existing values. Hence, whereas the entropy has the maximum but it is curved. Okay, means the cross entropy which is going to through this particular formula, okay, it is nothing but a curvature which will be showing you, which is allowing you to do the split where you can continue until the other nodes are going to be pure. Okay, so how it is going to work? With the classification error, the function is generally flat, something like this, which is going to, for example, if we are thinking that this is going to be a parent node, okay, then it is going to be a left node and this is going to be a right node at this point of locations that you are going to get all this stuff. So here, the final average classification error, whatever that you are going to try to identify, can always be the same as what you have got it as a parent node. Okay, so what it is going to be finally, which is resulting in the premature stopping. But we need something homogeneous at the end of the decision tree split. With the help of that one, we will try using the entropy gain, and instead of making on this particular line, we will go ahead with the parent node, which is going to be on the curvature line. So, and we will call something as a bulge. The function has something called a bulge. Okay, so here, this will allow one more line which is directly related with that part. Okay, which is allowing you the some average information of the children to be less than the parent. Hence, you are going to get some results in this information gain, and you will continue splitting the data exactly. We have one more thing called something called a Gini index. Okay, so the Gini index, classification error rate, and the entropy are the two different methods generally which will be used in the background in order to split the data based upon the data trees, say decision trees. So Gini index is generally the one which is being oftenly used for the splitting kind of purposes. So the Gini index reflects the lesser minimum, curvature of whatever that it is going ahead with across with. This function is also almost similar to the regular entropy function. Okay, this will also have the bulge when it is compared to the classification error, but this is not going to consider the logarithm. You are not going to have the logarithm factor here. Okay, so here the decision trees tend to overfit. Definitely, you need to check out this problem also. When your decision trees are going to be overfit or underfit, overfitting problem. Okay, so small changes in the data will affect the prediction and the high variance. So we need to check this one. So in order to fit the same thing, in order to do this one, why? Because the overfitting will cause the more number of nodes to be generated. When you have the more number of nodes, definitely there should be something needs to be done, which is called something called the pruning. Pruning is nothing but cut short all the branches wherever it is not required. Cutting short the branches will give you the more understanding about the current scenario. And the high variance you could see whenever you have the overfitting decision trees, there should be doing there we should be doing some sort of small changes in the data which will be giving you some sort of you know high variance predictions. The small changes in the data will affect the definitely prediction details of the results. So how to decide which leaves needs to be pruned? So we have the formula for that one, okay, based upon the classification error threshold that we can also keep an eye on. Okay, based upon the classification error threshold, you can always try minimizing the pruning the trees. I mean, you can always implement pruning the trees. Okay, so there is something called the strength of the what do you mean by the strength of the decision trees? See, it will generally interpret the data based upon if and else, okay, logic. So it can hand any data like ordinal, continuous, binary kind of stuff. So there is no pre-processing of the data is required or scaling is required. Scaling is required only for the guys. I already told you it is required for the some of the algorithms. I already mentioned you in the earlier session. Okay. So this is how generally the syntax that we will go ahead with. Okay. Scikit-learn. Okay. sklearn dot tree importing the decision tree classifier. Okay. This is a method that we will be using. Decision tree classifier is a method. And criterion, in our example that we went ahead with the entropy, here it was a Gini, okay, Gini index, okay, where you can always go ahead with one. Maximum depth, I already showed you what exactly this maximum depth is, and maximum features based upon the how many number of features that you are going to involve in the current line, I mean current problem scenario. Here you could clearly observe the depth understanding about the data. The more depth, okay, the more coverage of the data. So this is how that you will going to fit. Okay, fitting the instance on the data and then predicting the expected value. So DTC is equal to DTC dot fit means DTC is none other than, here we have created a variable called DTC, decision tree classifier, okay, which is taking three different parameters as the arguments. Okay, so here we can always predict the data from there on. So this is a very pretty understandable decision tree classifier where we will be understanding. Okay, tomorrow I will discuss few more concepts like a priori algorithms, and also uh, we have we have to cover the natural language processing and neural networks, artificial neural networks. Okay, so tomorrow and day after tomorrow, I will try to cover it up. And as I told you that I will be sending you the project report, otherwise, project data set, project related data set, and the problem statement. I will be sending you today in the afternoon around. Okay. Any questions so far, guys? Anusha, Ram, Dinesh, Sunil, Suresh. Any questions? Okay, I will take it as no questions then. Okay, we will meet again tomorrow and we will discuss about the random forest and followed by the a priori algorithm stuff. Okay, see you all. Bye.